We now take a look at the Rapid Spanning Tree Protocol, or RSTP, that represents a number of improvements on the original Spanning Tree Protocol. The original STP standard was defined in 1998, for which a number of limitations were discovered, particularly in the time needed for convergence to occur. In light of this, the Rapid Spanning Tree Protocol, or RSTP, was introduced. The fundamental characteristics of RSTP are understood to follow the basis of STP. Therefore, the characteristic differences within RSTP are emphasized within this section. So upon completion of this section, it is generally expected that trainees will be able to describe the characteristics associated with RSTP, as well as configure RSTP parameters. In reflection of the original Spanning Tree Protocol, we find that one of the biggest drawbacks to the protocol is in the time taken for the switch network to converge. This can be greatly damaging to the smooth operation of many network services, which is exemplified by the fact that recovery of the network results in the convergence effect being repeated. The main goal of RSTP is to tackle this problem of slow convergence time and provides an effective solution through the removal of reliance on timer mechanisms within the spanning tree and applying a method known as proposal and agreement that allows a network to converge through a negotiation process that originates from a root bridge and cascades segment by segment through the network until all switches are in agreement. The RSTP topology, in addition to the designated root and alternate ports, defines a fourth port role referred to as the backup port. We should understand that the role of an alternate port is to represent a redundant path that leads back to the root bridge, whilst in comparison, the backup port is assigned to represent a redundant path that leads away from the root bridge, such as in the case of a redundant link on a hub as shown in this example, that connects to what is referred to as a leaf node or end station. The RSTP edge port is designed to allow ports on an RSTP-enabled switch that connects to non-STP devices, such as end stations, to instantly transition to a forwarding state. This is done to prevent unnecessary forwarding delay to the end station, since devices connected to edge ports do not participate in STP and therefore will not generate switching loops. In the event, however, that the edge port happens to receive configuration BPDU for whatever reason, the edge port will lose its status and transition to a common STP port and go through the STP convergence process. Whilst edge ports are a feature of RSTP, it is also possible to apply this feature in STP when using Huawei switches. We represent here the port states used in the STP protocol and compare those to the port states that are represented in RSTP, along with the typical port roles associated with each port state. The change in port state occurs since there is no longer a need for forward delay periods that give the topology time to converge, and so instead we see in the case of RSTP only 3 port states of discarding, learning, and forwarding. The backup port is considered to take on a discarding state, which is the equivalent to the blocking state in STP. While in a learning state in RSTP, the switch will again learn MAC addresses, and in the forwarding state will begin to forward user traffic. While the original Spanning Tree Protocol included 2 forms of BPDU, RSTP only employs a single type of BPDU that contains additional parameters to support the features of RSTP. In particular, we find within the flags field of the RST BPDU additional parameters in the form of proposal and agreement flags, fields that carry information regarding the port role as well as the port state. One of the main alterations to the behavior in the spanning tree process is in the propagation of BPDU. The original method involved the root bridge being responsible for the generation of BPDU and the propagation of BPDU occurring downstream from the root bridge. In RSTP, however, the generation of RST BPDU is the responsibility of the designated switch for each segment. This is possible since convergence is performed on a per-link basis rather than on convergence of the entire switching network. We understand from the example given here that switch B is able to generate RST BPDU at intervals independent of the RST BPDU generated by switch A. The general convergence process of an RSTP-based topology follows the same principles of spanning tree, in which all switches assume the status of root bridge at the point of initialization and must communicate with neighboring switches to assert this status. The port role of each switch is again set as designated and operates initially in a discarding state. The method used to achieve convergence, however, differs from that of the spanning tree protocol. The convergence process is initiated by each switch sending RST BPDU via designated port interfaces. In this example, we demonstrate a single instance of this in which an RST BPDU is generated and transmitted by switch A to assert its position as the root bridge and designated switch for the segment. The RST BPDU transmitted is considered a proposal since the proposal bit in the BPDU flags field is set. After receiving the RST BPDU, switch B will proceed to assess the BPDU to determine whether the bridge ID is superior to its own. If not, the RST BPDU received will be discarded and switch B will continue to generate its own BPDU. If the received BPDU is superior, switch B will begin a process of synchronization. The synchronization process is designed to allow the convergence of a segment to occur without risk of switching loops occurring. Upon recognizing that a superior BPDU has been received, the switch, which in this case is switch B, will need to set all other designated ports to a discarding state in order to prevent the forwarding of any frames during the proposal and agreement process. Following the blocking of all downstream designated ports, an RST BPDU is returned via the port on which a proposal was received. The returned BPDU confirms that an agreement to the proposal has been made, and is further asserted by the fact that the RST BPDU now contains the port role of root, as well as the setting of the agreement flag within the flags field. The information carried in the RST BPDU containing the agreement allows for the synchronization of the segment, that in turn safely allows, on this segment at least, for the forwarding of data to begin. Switch B will now assume switch A to be the root bridge, and will begin the same proposal and agreement process for the downstream segment, using the same fundamental negotiation parameters as used within the original STP. Since the path cost is equal, the proposal and agreement will again fall back to the bridge ID for agreement on the designated switch for this segment. The effect of failures in a switching network using RSTP no longer relies on the max H time to timeout connections, but instead is based on the equivalent of 3 consecutive BPDU, which are transmitted at an interval based on the hello timer. This by default means that the time to discovery of a failure is shortened, following which the proposal and agreement can again take place. The example given here demonstrates a loss of BPDU from switch A that effectively causes a renegotiation of the root bridge between the 2 remaining switches through the same proposal and agreement process. We demonstrate here the effect of link failures on the spanning tree network when using RSTP and the minor differences that occur. This example demonstrates a failure on the link between switch A and switch C. This effectively will cut off switch C from the receiving BPDU from switch A. The loss of the link will immediately be detected by switch A and C, for which both switches will proceed to flush the MAC addresses for the respective ports on that segment. Switch C will begin to negotiate its role in the network following loss of connection to switch A. This is done through the proposal and agreement process on the segment with switch B. Since RST BPDU from switch B contains the root ID of switch A, it is switch B that will provide a valid proposal to switch C that will return an RST BPDU containing a set agreement bit as well as a set topology change bit to inform of the need to flush the MAC entries for all upstream interfaces, with the exception of the interface on which the RST BPDU are received. New MAC entries are then relearned based on the new spanning tree topology. Where a spanning tree topology contains a mix of RSTP-enabled switches, as well as switches that are still supporting STP, it is possible for some level of compatibility. This is achieved by the RSTP-enabled switch automatically rolling back to use the more traditional form of STP. However, in doing so, the switch is again subjected to the effects of STP, including the timer period that may result in an extended downtime once again while the network converges. It is therefore recommended that the network supporting RSTP not contain any STP-enabled switches. RSTP is enabled by setting the mode within the switch using the command stp mode RSTP. As mentioned in the section on STP, the default mode is MSTP within VRP, and therefore this command needs to be set if RSTP is to be used. Each switch in the spanning tree topology must be configured with this command to ensure a complete RSTP-enabled switching network. The display STP command can be used to verify that RSTP has been enabled as the current protocol used on the switching device. The same principles apply as was demonstrated for STP, and enable us to determine the root bridge as well as the designated switch for the segment. In this instance, we can see that the displayed output is that of the root bridge. For port interfaces that are not participating as part of the spanning tree topology, such as in the case of the port interfaces that are connected to end stations, the edge port enable command can be applied. In doing so, the port will immediately transition to a forwarding state, since port status negotiation is not required. This command will apply to a single port interface as shown in this example, and is configured under the port interface view. Where it is required that multiple ports be configured for operation as edge ports on a single switch device, the STP edge port default command may be used. As opposed to the edge port enable command, this command is configured under the system view and will apply to all port interfaces on the switch. It is likely, however, that not every switch interface will be operating as an edge port, and a minority of switch ports may need to participate in the RSTP calculation. As such, the edge port disable command should be used on a per interface basis to allow RSTP to operate on these select port interfaces. For those interfaces that have been configured to operate as edge ports, it is generally expected that these ports be excluded from the spanning tree topology. If, however, a BPDU is generated on the edge port interface, either as a result of malicious activities or because a rogue switch was introduced to the network, the port interface may suddenly be readopted as part of the spanning tree topology, and convergence may occur that affects the current and often carefully planned spanning tree design structure. The STP BPDU protection command enables protection against these BPDU by shutting down the edge port in the event that a rogue BPDU is received. Once a switch port is shut down, reactivation would require administrator intervention. The command is applied on a per switch basis and configured from the system view. In some cases, the integrity of the spanning tree topology may be affected by other factors, such as link congestion that hinders the delivery of BPDU to the downstream switches, or unidirectional link failure that occurs when the wire circuit fails on a twisted pair of the Ethernet medium. But since the other wire is still active, the link continues to show as up. In either case, the downstream switch may fail to receive BPDU and cause the block ports to transition to a forwarding state, causing spanning tree loops. In using loop protection on the root port interface, the root port will enter a blocking state in the event that BPDU fail to be received, and stops transmission of frames in order to prevent the possibility of loops occurring. We can go on to verify the resulting implementation of the commands implemented on the root port of interface gigabit Ethernet 0/0/1, for which we were able to verify the port role and the current protection type that has been applied to the port interface, which in this instance is the loop protection mechanism. The edge port configuration in this instance is not applied to port interface gigabit Ethernet 0/0/1 since it is participating in the spanning tree, and so the port edge status shows as disabled. Where a port is operating as an edge port, however, the config and active states will both display as enabled. In summary for this section, then, we just have one question here which asks, what is the purpose of the sync that occurs during the RSTP proposal and agreement process? Well, it is the purpose of the sync operation to ensure that loops do not occur during the convergence that results from this process. It basically achieves this by blocking any ports that are participating in the spanning tree topology and are capable of forwarding BPDU, which simply relates to all designated ports pointing downstream. Once convergence is complete, however, the block ports will return to an active state.